The second problem of the same type is car negotiating a turn on a banked curve. Banked meaning that it's not flat, it's at angle. In this case, I will look at the scenario when the surface is frictionless. And in the next question, there will be some friction. When the surface is frictionless, the car, you could imagine, will slide off the curve pretty much right away. And the only way to not have that happen is for the car to continue to go at a certain speed around the curve. So this view is, for example, a car moving away from me. This view is from the side, not from the top. The car is moving away from me. This is the radius of the curve. This is the angle of the surface. And centripetal acceleration is pointing towards the center of rotation. As I mentioned, the surface is frictionless, so I'm not drawing any friction here. So let's see what's given. Mass of the car could be given, not that we need it. Hold on. Angle theta should be given. Radius should be given. Question generally says what speed the car needs to maintain such that it doesn't fly off the course, not forward to the center, not completely out of the track. This is what we will do. We'll start by writing the same equation as before, that the sum of all forces acting on a car equal MAC. And the two forces acting on a car, normal force, gravity force, we need to resolve them into X and Y. That's the time when I will say again that X-axis should be pointing into the same direction as acceleration. This is not how we used to do it before. Usually we would go along the incline. But in this case, it's pointing the same way as acceleration. So when that happens, Y is pointing up. And let's see what components will be. Normal force will have components. The X component is right here, this piece. The Y component is right here, this piece. And it can be proven, but judging by the looks of it, angle theta is the smaller angle. So when I write components for X, normal force will be n sine theta. Mg does not have any effect horizontal. MAC, and AC we know how to find, V squared divided by R. We'll get there in a second. For Y component N, which is kind of the same piece, will be N cos theta. Mg pointing the other way. And AC does not produce anything. It's a 0. So let me rewrite the second one. Yes. First one will stay as is. And sine theta equals MAC. The second one will be N cos theta equals Mg. So that's my system. I will divide one over the other. Divide top by the bottom. Sine theta divided by cosine theta. When I divide n and n, they will cancel each other. And m will cancel each other. So it was like n, m, but this cancels and that cancels, so I'm not even writing any of them. So it's only AC and G. Sine over cosine is tangent. And AC is V squared divided by R. So from here, we will be able to find the V that's needed for the car not to fly off the course. R travels here and take a square root out of this expression. Now you can imagine any radius you want, within reason, obviously, any angle you want. Usually it's less than 10 degrees, but you can imagine, and then you will be able to calculate V. And that's how we would solve the problem when the curve is frictionless. The next problem will be with friction, and the solution will be quite lengthy. So stay tuned.